So last time we ended with section 1.3. We were halfway through it, talked a little bit about what a function is and what it isn't. So remember, if it fails the vertical line test, it's not a function. So we're going to start out by just graphing a function on the calculator and figuring out what the domain and range is. All right, so domain and range is something we're going to spend some more time with this week. So when you think domain, what letter in your function is the domain? It's your x, okay? It's the values you are allowed to plug in. And the range is your y, right? It's the answers that the formula gives you after you plug something in, right? So let's graph that and see what the domain and range is, right? All right, so it's 16x minus x cubed. Let's type it in. So 16x minus x cubed. I'm just going to do zoom 6. Start with a standard window. Is that a good window?
No.
No, because remember, a cubed graph can turn how many times? Twice, one less than the highest exponent. I can see it's turning, but the turns are off the screen. So let's try, like, since they're off the screen up and down, let's try making that like -40 to 40. And you could try other values. I'm just guessing. Actually, that's fine. So that's a good window. Right. And now they want me to determine the domain and the range. So the domain is how far left and right this graph is going to go. What do you think the domain is here? Yeah?
All real numbers?
Yeah, it's all real numbers. You really don't even need to look at it to figure that part out. Look at x here and here. Ask yourself, is there any number you can't multiply by 16? No. Is there any number you can't raise to the third power? No. You can raise fractions, decimals, positives, negatives. You can raise all of those to the third power. The only time that there's not something in the domain is if you have a square root. You've got to be careful you don't take the square root of a negative. And if you have a fraction where you could divide by 0. Neither one of those things happen here.
My graph is like off center, like weirdly to the right.
Hey, did you adjust your window?
Yeah, I got the.
You got your window.
I lost a 0.
Okay.
Alright, never mind. You good?
All right. All right, so domain here, all real numbers. So you can write it, I'm going to write it 2 ways for you. All reals is how you can write it in words, or go like this. We're going to start, we'll see that notation a lot more this week. -infinity to infinity. That's the lowest, comma, the highest. All right, now the range. The range is up to down, okay? It's the y values. What do you think the range is in this graph? It's also all real numbers, okay? Because the graph is going to go down forever. It's going to go up forever. And this kind of graph is what we call continuous. You never lift your pencil when you draw it. So if it goes down forever and up forever, and you never lift your pencil, you're going to hit every single value up and down forever. So the range is the same thing. All reals. And it's -infinity to infinity. Okay, any question on that? Yeah?
Why do you always put a negative on the first infinity?
Because it's -infinity to positive infinity. So like, in terms of domain, -infinity means it goes left forever. Positive infinity means it goes right forever. In terms of range, -infinity means it goes down forever. Positive infinity means it goes up. Does that answer your question? Yes. Okay.
Just one question.
So for a window, I started with a standard window, and then I changed it to -40 to 40 on the y's. Just so I could see, because it technically said find a complete graph. So complete graph means you should be able to see like all the turns that it's making and stuff like that. Okay. Any other questions or trouble getting that graph on the calculator? Okay. All right, so let's look at this problem. So this problem says that we have a rectangular pool, and the dimensions of the pool are 30 by 50 feet. We're going to put a sidewalk around the pool, and the sidewalk is going to be the same width all the way around. Okay, I don't know what the width is going to be, but we'll call it x. Okay, so even though we don't know what the width is, they tell us that the area of the sidewalk is going to be 600 square feet. So knowing the dimensions of the pool and knowing the area of the sidewalk, we can figure out the width of the sidewalk. All right, so what could we do that would make this problem easier to kind of visualize? Yeah? Yeah, I would draw a picture. That way we don't have so much in writing that we're trying to figure out where we can actually see it. I think that'll make it easier. So I'm going to start with a swimming pool, and then I'll put a sidewalk around it. So I'll try to keep that on the screen too. So here is the swimming pool, sidewalk around it. It's supposed to look like it's uniform width all the way around. It's close enough. What are the dimensions of the pool again?
30 feet by 50.
30 feet by 50 feet. Okay, so 30 by 50. And the width of the sidewalk we don't know, and what did they tell us to call it? Yep, we're going to call it x. Any questions on that picture? All right. So we're dealing with rectangles and area. So we're going to need the formula for area of a rectangle. What's the formula for area of a rectangle? Yeah, go ahead, Jared.
Length times width.
Length times width. Right, now I'm going to give you a little bit of a hint. Let's say that I wanted to find well, we have three things. We'll call it the big rectangle. Okay, that's the one on the outside. We have the pool, and then we have the area of the sidewalk. So we have three different areas in this problem. Let's say the area of the big rectangle. How would you find that? Based on the other two shapes I mentioned, the pool and the sidewalk.
Of the pool or the whole thing?
I want to find the area of the whole thing, that big rectangle. So the area of the big rectangle would be what? That we already know the areas of. Yeah?
You take the area of the pool
Okay.
plus the area of the sidewalk.
Yeah. Perfect. Take the area of the pool plus the area of the sidewalk. Okay. Let's fill in what we can. And at some point, we're going to have some variables because we're not going to be able to figure out the area of the big square, big rectangle. And that's going to be the variable we need to solve for. All right, let's start with the area of the pool. Okay. How about Brandon? What's my calculation for the area of the pool?
Do you want the number? Like how to do it?
Just tell me how to do it.
30 times 50.
Yeah, 30 times 50. And what does that give me if I do that out?
1,500.
So we get 1,500. Plus, Eric, what's the area of this sidewalk?
600.
Yeah, they tell us that, right? Area of sidewalk is 600. Okay, those are the easy two. Now we have to figure out the formula for the area of the big rectangle. All right, and remember, it's length times width. So we're going to have a length and a width. So first thing I want to know is the length of that line in red. Well, is it more than 50 or less than 50?
More.
Yeah, it's more than 50. So my suggestion would be, I'm going to look at it like that. I would think they could tell me how long that rectangle is.
At least 50 feet.
So it's 50, yeah, plus how much more?
Maybe 20.
Well, we don't know. That's the thing. We're not going to have a number for how much more. How much is this little part right here?
Well, that inside portion is 50 feet.
Yep, so this part inside is 50. But then how about the two parts on the outside?
We don't know yet.
We don't have a number for it. But do we have a way to represent it? Yeah,
BX.
it would be x. It's the width of the sidewalk. And the width of the sidewalk again. So how long now is the big rectangle? Yep, Elias. It's not going to be a number.
Oh.
Yep.
50 plus 2x.
50 plus 2x. That's the length of the big rectangle. And how about the width? What's the width going to be? Yep, Kaya? 30 plus 2x. Now we've got an equation set up. We just got to distribute some things out and simplify, and then we can solve for x. But first, any question on just setting up the equation? All right. How about Chris on the right-hand side? When I do that out, what do I get?
The red part?
The right part, yep.
25 plus, wait. 5 plus X.
On the right side?
5 plus X.
So on the right side, we don't have any x's. Do you know what I mean by right side? 1500 plus 600. On the right side of the equal sign.
615. Wait. Oh, sorry. 2100.
2100.
Sorry, just look at the left side.
All right, now we got to do the left side. I did the right side first because that side, that's a little simpler than the left. On the left, there's a word for doing this out. Does anyone know what word I'm thinking of? Some teachers teach this, yeah? Yep, we got to FOIL it. So we got to start with 50 times 30. And Jacob, how much is 50 times 30?
1500.
Yep, 1500. So actually the 1500 we had here and we had on the right, they're really just going to cancel each other out. We already combined them, so it's fine. Doesn't matter. And then 50 times 2x. Michaela, how much is that?
So 50 times 2x?
Yeah.
100x?
So we get 100x. And 30 times 2x. Yeah.
60x.
60x. So 100 plus 60 is 160x. And the last part, Sam, what's 2x times 2x?
4x squared.
4x squared. Good. Great. Now, looking at that equation, focus on the highest exponent. That'll tell you what kind of equation this is. What kind of equation is that? Well, what is the highest exponent?
2.
2. And any equation that has a 2 as the highest exponent is a, yeah?
Parabola.
The graph of it's a parabola, but the equation itself is a, it begins with a Q. It's a quadratic, yeah, it's a quadratic equation. So when we want to solve a quadratic equation, we don't want it equal to 2100. We want to get it equal to what number? Anytime you solve a quadratic. Yep, always get it equal to 0. So I would move everything to the left by subtracting. Now we have nothing on the right. And when we write a quadratic equation, we usually put the squared term first, then the number with x, then the number without x. So let's put it in that order. 4x squared plus 160x, and Caleb, 1500 minus 2100.
Negative 600.
Yep, negative 600. Good. Now, before we solve that, there's one thing you can do to make these numbers a little easier to work with. Does anyone see what you can do in this equation? Yeah?
You can divide by 4.
Yeah, you can divide everything by 4. And it doesn't change the answer, it just makes when we do the calculations, our numbers are a little bit smaller. What's 160 divided by 4? Yep.
40.
Yep. Good. So 40 and 600 divided by 4?
150.
150. Okay. Now, one way you can solve a quadratic is to factor it. Factoring will not work here because you're not going to be able to find two numbers that multiply to give you 150 and add or subtract to give you 40. Not nice numbers. Okay, so it's not going to factor. What's another way you can solve a quadratic if it doesn't factor?
Can I grab the
All right. So, what's another way you can solve a quadratic equation if you can't factor it? Yep.
Substitution.
You can do substitution when you have like a system of equations, like y equals 2x plus 7 and y equals 8x minus 5. Then you can use substitution to solve. But what else could we do here? What kind of equation is that again?
Quadratic.
It's a quadratic. So there's something else that exists to solve quadratic equations.
Oh.
Yep.
Quadratic formula.
Yes, the quadratic formula. So that was the easy part, I hope, remembering it. Now the hard part is what actually the formula is. Does anybody remember the letters that are in the formula? There's 3 of them. So I'd be really happy if we just know the letters. Yeah.
A, B, and C.
Right, there's an A, B, and a C. So the formula, negative B, plus or minus. Does anyone remember what comes next? That's actually
That's on the bottom, right?
bottom, yep.
It is A squared.
B squared.
Or B squared. The letter off. Plus like A minus C squared.
Close, it is a minus. It's a minus.
8 times.
It's part of it, and then there's a number in front of it. Anybody remember the number that goes there?
4.
4. So it's negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now, in my problem, what are a, b, and c? A is 1, yep.
B is 40.
Okay.
C is negative 150.
C is negative 150, yep. Okay, so now just plug them in and see what we get. And this will tell us the width of the sidewalk. Now, actually, before we plug it in, how many answers is this formula going to give you?
2.
2. The width of the sidewalk, though, can only be how many answers? 1. So one of the answers is going to make sense, one of them won't. So negative b plus or minus the square root of b squared, I'm just going to do that as we go. 1600 is 40 times 40. Minus 4a c, all divided by 2 times 1. Okay, now under the square root, we're going to be subtracting a negative. And when you subtract a negative, what happens to it? Okay, it turns positive. So I'm just going to make that positive right now. So negative 40. 4 times 1 gives me 4, and 4 times 150. And 600 plus 1600. 2,200. Okay, so 2,200 divided by 2. Now at this point, we have to just type it in and see what we get. Okay, so x is approximately, let's type it in. Let's see. Bless you. I'm going to do the top first, so negative 40. I'm going to do the plus. Square root of 2,200. And when you do the top, you get that. And then divide by 2. So about 3.45. Now, let's do the other answer. Negative 40 minus the square root of 2,200. And why can I pretty much stop right there? I need to still divide that by 2, but how come that doesn't matter? It's negative, and if I divide it by 2, it's like negative 43 or somewhere around there. You can't have a negative width in this problem. Okay. So that is the width of your sidewalk. Just under 3.5 feet. Okay. So any question on how we figured out the width of the sidewalk? So the key was really being able to set this up. You had to figure out an equation to set up. Then you had to solve it. Any questions? All right, so that's a formula you should, we'll talk about it a couple more times, but we definitely, we need that formula for a lot of stuff. All right, so projectile motion. So throughout the first few chapters, we do a lot of problems that come back to projectile motion. Projectile motion is basically like if you took an object and you threw it, and it traveled like that. The idea with projectile motion is after you throw the object, gravity takes over. Now, we're going to look at a formula for projectile motion that's actually, it's 3 terms, and it's pretty accurate. All right. If you were really launching something a long distance, and by long distance I mean like, say you launch something from like Boston to England, this formula, it wouldn't quite work. Okay, but for small distances, like the length of a football field, or even like halfway across a city or something, it would be fine. Okay, and that's the formula. So it says the height, that's what this is. That's the height. So the height of the object equals, and now what you have to do is plug in some stuff. Okay. Negative 16t squared plus v sub 0 t plus s sub 0. So there's 3 variables, t, v sub 0, S sub 0. T is time. Okay, that's what it says up above, in seconds. V sub 0 is the initial velocity. So like if you were throwing a baseball, the second it leaves your hand, how fast is it going? And S sub 0 is the initial height. So if you were throwing a baseball, maybe it would be released like 4 feet off the ground, or whatever. If you were launching something off a building, maybe it would be the height of the building. Now, is anyone taking physics? So,
Last year.
if you took it last year, you probably saw the number like 9.8 a lot. 9.8, you can use that number if you're dealing in meters per second. When we're dealing with feet per second, we use negative 16. Okay, so yeah, in physics 9.8, or maybe it's half of 9.8, but anyway, the 16 comes from the acceleration due to gravity, okay, in feet per second. So, in our problem, we've got a model rocket. It's being shot straight up from ground level, and it has an initial speed of 64 feet per second. Now, in real life, there's all kinds of things that would complicate this. The rocket isn't going 64 feet per second like instantly. There's a time of acceleration. And then there's also air. Air resistance is going to slow it down. But we're not going to deal with all that stuff. Okay, so there's our problem. And the first question they ask us is, at what time will the rocket be 50 feet above the ground? Well, before we can answer that question, what do we have to do? What would be our first step towards answering that question? Yeah.
Plug everything into the equation.
Yeah, we've got to plug everything in. Okay, we're going to make the equation first, and then we'll have something to solve. All right, so S sub t is the height. All right, we can fill that in a minute because we know it's going to, well, we can fill it in now. We want the height to equal 50 feet. So that part of the equation is 50. Now let's start filling in the right-hand side. Negative 16. Are we filling anything in for t? No, that's the question. What time? So we don't know t. Plus, the next term is v sub 0 t. My initial velocity times my time. What do I fill in for my initial velocity? Chris? Yep, 64 t. Plus the last term is the initial height of the rocket. What's the initial height of our rocket? 0. This rocket is being shot from ground level, so there is no initial height. It's plus 0. Okay. Any questions on that? Now, what kind of equation is that again? It's a quadratic. So we could solve it just like we did before with the quadratic formula. Or let's do it a little different. Okay, let's do this one on the calculator. So what I'm going to do is graph what's on the left in y1 and graph what's on the right in y2. Okay, what I'm basically doing is I'm putting a horizontal line at 50. And then I'm drawing a parabola. I'm going to draw those two pictures at the same time. And then we'll go from there. Now, I'm going to do zoom 6. Is that a good window?
No.
No. What do I need to fix?
Need to move it up.
Yeah, I got to go up a lot higher. Okay. I got to go up at least as high as how much?
50.
50, because that's what we're looking for, but maybe the rocket goes even higher than that. So let's put like, I don't know, let's put 75. So there's my line at 50. There's the rocket. And that's fine. Obviously, there's some values that don't make sense, like negative time. Really, that doesn't make sense. Neither does negative height. Okay. So you really just want to focus on quadrant 1. So now, how would I find where this equals that? Not using quadratic formula, using my graph now. Yep.
Look at the intersections.
Yeah, look at the intersection. So second calc, intersect. Pick a point on the blue, the red, and now put your guess closer to the one you want. Okay, I'm doing the one on the left. If someone else can do the one on the right, that'll be helpful. So at 1.06 seconds, the rocket would be at exactly 50 feet. That's one time. And what's the other time that it hits 50 feet? Yeah, Jared?
2.94.
2.94. Thank you. Seconds? Seconds. How come the rocket hits 50 feet twice? How does that work? What's happening? What?
It goes up to 50 feet altitude, then goes past it, and then descends down back to 50 feet again.
Yeah. So unless 50 feet was the very maximum that the rocket hit, it's going to hit it twice. It's going to hit it going up. It's going to hit it coming down. Perfect. Okay. And these are the two answers you would have gotten with quadratic formula, plus or minus. That's where the two answers would come from. All right. What is the maximum height, and at what time is the maximum height reached? All right. So let's go back to our graph. So you can really ignore the line in blue. If you want, you can get rid of it. Okay. All right, so let's get rid of the 50-foot mark. We don't need that. And I don't know if we've used it yet here, but it's under calculate, second calc, maximum. Now, this question is asking two things. When does it hit the maximum height? What is the maximum height? So let's go to second calc maximum. Pick a point that you know is to the left of the maximum, okay, and then hit enter. It puts in a dotted line. That's kind of like a barrier. It's going to look between there and go to the right of the maximum and hit enter. So it's going to look between the dotted lines. There's only one maximum in there, so the guess doesn't really matter. Hit enter, and it gives me this. I wanted to see if I could. Yeah, that's what I wanted. All right, let's move it down so you can see it. So what is the maximum height? Should you be looking at the x or the y?
Y.
You're looking at the y. Remember, the variable, the x, that's my time. The y is what it's equal to. That's my height. So the maximum height is how much? 64 feet. And this occurs at what time?
Basically 2 seconds.
It occurs at 2 seconds. Now, if you were to actually figure this out, you might be able to do it with algebra. You could definitely do it with calculus, this maximum. You would get an answer of exactly 2 seconds. All right. The reason we don't on the calculator is because the calculator can't really do algebra. The calculator can guess a bunch of numbers really, really fast, and that's all the calculator can do. But if you can guess millions of answers per second and check each one, I mean, you're guessing so fast, why do you even need algebra? So that's basically what the calculator does. So that's why it's 1.99999. Right. So this occurs at 2 seconds. Now, let me just copy that down for a second. Negative 16t squared plus 64t. I'm going to show you, you don't have to know this, but I want to show you how easy it is to get 2 seconds using calculus. So I'm not going to explain all the steps, I'm just going to show you how many there are. First step is to set it equal to 0. The second step is to take what's called a derivative. You don't have to worry how I did that. What I basically did is I just multiplied negative 16 by 2 and got rid of the t there. You don't have to worry. And watch my last step. Bring the 64 to the other side. Divide by negative 32. Divide by negative 32. Negative 64 divided by negative 32 is 2. So what I just did there was calculus. And the reason I showed you is because some people think, oh my god, calculus is really like always difficult. I think I found the maximum here quicker than I probably did on the calculator. If I wasn't trying to explain what I was doing, I definitely could have written this faster than using a calculator. Right? We're not doing it this way in this class. Right? We're just going to stick with the calculator. Right? But it's not that hard to do it other ways. All right. Any questions on how we did it with the calculator? All right. So last thing, and then we'll look at that. So a piecewise defined function. This is basically just going to be something we do on the calculator. It's where you draw 2 functions on the calculator screen pretty much at the same time. So the idea in a piecewise defined function is that you don't just give me one formula to use, you give me 2 or more. And there's conditions on when you use which one. So here is an example of what a piecewise defined function looks like. It says f of x equals, and notice there's not just one formula, there's 2. Which one do you use then? Well, they tell you. If you give me a number less than 1, I'm going to use the top formula to get the answer. If you give me a number greater than or equal to 1, I'm going to use the bottom formula. So I use a different formula depending on the value of x. And you can have more than 2. You could be like, well, use this formula if x is this, use this formula if x is that, use this formula if x is that. Okay? But that's the idea of a piecewise defined function. You have different function rules depending on your value of x. But generally, when you set up a piecewise defined function, no matter what value of x you give me, there's a place for it somewhere in the formula. Is there any value of x you could give me that wouldn't fit in either the top or the bottom formula? Yep.
0.
Well, 0 is less than 1, so it would go on the top of it. What do you think? Is there any value of x you could give me that wouldn't fit one of these 2 conditions? What do you think, Eric?
There is.
No, no matter what number you give me, it's either going to be less than 1 or it's going to be greater than or equal to 1. So it's going to fit into one of these formulas. All right, so let me show you, like, if you were graphing this, what you would do. If you type this in, okay, just watch this for a second. You're going to get a parabola. Let me do zoom 6. Okay, so you get a parabola, but it draws the whole parabola. I only want to draw this parabola when I'm less than 1. So I want the parabola to cut off, like right there. I want it to just draw it and stop. And that's it. So the way I can do that so the way I can do that is what you're typing in parentheses. The parentheses are important. And then next to it, you're going to put when you want it to draw that. X, and this is new, second math. If you press second math, it'll bring up a menu of inequalities. We want less than 1. So now it's going to draw that parabola, but it's only going to draw it when x is less than 1, and then it's going to stop. Okay? So watch what happens. There's your parabola, boop, it just stops. Now, I know it's drawing this line here on the axis. That line in blue shouldn't be on the axis. I can't get rid of that. But it draws the parabola, and then it stops. All right, so that's the first part. And let's do the second part. Okay, so now I'm going to take an x cubed minus 4x, but again, put it in parentheses. X cubed minus 4x. And we want to do that when x is greater than or equal to 1. Second test, greater than or equal to 1. Again, the part where it draws it on the axis, that should not be there. So, put that over here and show you what it should actually look like. Okay, I'm just going to draw over that part in black. Okay, so there's your axis. Close enough. So it's two separate graphs. You just have to put it in parentheses. But that's how you type in a piecewise function. Any question on that? Sometimes piecewise functions connect, sometimes they don't. This one doesn't connect. Just the way it is. Okay, so any questions? Yeah.
Confused on how you get into the you put the equation like 3 minus x squared, and then you also have to put that.
Yep, you have to put everything in parentheses, just like that. Yep. If you don't put parentheses, then, well, try it. Take the parentheses out. It won't work.
And you get x cubed, you only get x squared.
X cubed. So you want to press the caret and then 3. Yep. So just press the caret key and then press 3. Okay. So last thing we're going to take a look at is something you've definitely done before, which is like slope-intercept. So we're not going to spend a ton of time on it. Where in Algebra 1, I might spend a couple days going through all this stuff. Slope-intercept form of a line. Can anyone remind me what that equation is? It starts out y equals, yep.
Y equals mx plus b.
Yep, and what does the m stand for?
The initial value. No, I know the x is. I forgot. Sorry.
M is slope, yep.
Yeah.
And how about the b?
Y-intercept.
Yep, y-intercept. So if you already know that, don't worry about it. You don't have to write it. But m is slope, b is y-intercept. Now, that is called a linear function because when you draw something in y equals mx plus b, it looks like a line. We've looked at graphs that are way fancier than this. We've looked at things that curve and turn. These are the simplest, just a straight line. Now, m and b, this says right here, m and b are elements of the real numbers, meaning your slope and your y-intercept can be any real number you want. Positives, negatives, fractions, and decimals. The only thing your slope can't be is 0. Because if you fill in a 0 for your slope, you wipe out that whole thing. Now you don't have y equals mx plus b anymore. You have y equals b. Right? That's kind of like when we did the projectile problem and we graphed y equals 50. That's a horizontal line. That's different than y equals mx plus b. Still a line, but it's not on a diagonal. All right. So for this one, what I would do is you can really abbreviate. You don't have to write down this whole problem. But the idea is that a house was purchased 10 years ago and it was worth $60,000. And then 10 years later, it was worth $85,000. We're going to assume that there's a linear relationship between time and the value of the house, meaning it went like this. Value of the house, it just went straight up. Well, not straight up, but it went up linearly.
Steady increase.
Yep, steady increase. Same slope. Find an equation that represents this situation. Okay, I just want to find an equation. Now, I mentioned the word slope. Okay, so slope is going to come up here. You're going to have to find a slope. And does anybody remember what your formula for slope is? It's the m in the y equals mx plus b. How do you find slope? Yeah.
It's like changing y over changing x.
Yeah, that's exactly what it is. It's change in y over change in x. So change is the difference. So y2 minus y1, find the difference between that, over x2 minus x1. Now, we just need to make some coordinates here. And it's going to be time, comma, value of the house. So, when we first bought the house, at the very beginning, how much time had passed? Like right at the very beginning when we bought the house. You could think of that as like it's the start. 0. No years had gone by yet. The day you bought the house, it was worth $60,000. And then, how many years go by in the problem? 10 years go by. And what's the value of the house after 10 years?
$85,000.
It's worth $85,000. There you go. There's your coordinates. So now we'll just find the slope. And then we need the y-intercept, but that should be pretty easy to get here. So let's do the slope first. Y2 minus y1. What's 85,000 minus 60,000?
25,000.
25,000. And now in the bottom, x2 minus x1. What's 10 minus 0? 10? So 25,000 divided by 10, just take off a 0. It's going to give me 2,500. So that's the rate of change of the value of the house. $2,500 a year, basically. Now, we've got the slope. What's my y-intercept? Yeah.
0.
Well, it's the y value when x is 0. It's where it crosses the y-axis, this line. Yeah.
60,000.
Yeah, good job. 60,000. So you've got m and you've got b. Just fill them into the equation I just gave you. Y equals mx plus b, which is 60,000. Now, if they wanted to know when the house was worth $71,000, where would the 71,000 get plugged in? For y or for x?
Y.
For y. Yeah. X was time. Y was value. So all you do is plug in 71,000 and then solve. Subtract 60,000 and divide by 2,500. Any question on that? But that's your equation. Now, there's two special slopes. It didn't come up in this problem. But you have a perfectly horizontal and then a vertical line. If your line is perfectly flat, what's the slope of it? Yeah.
0 over 1.
Yes, 0 over something, which would just be 0. Now, what if your line is vertical? What's your slope in that case? Yeah, Emily?
Anything greater than 1?
Well, if it's a number, it's going to be on a diagonal. So from your perspective, like that, positive slope. But vertical is something special. You would know it's as steep as you can get. Yeah.
Is it just y equals x?
So y equals x, that would be a slope of 1. That'd be like y equals 1x plus 0, no intercept. Yeah? Kind of. There's another word we use when we talk about a vertical slope. It begins with a U. Remember that one? Undefined. So vertical line slope is undefined. Because if you tried to find the slope of a vertical line, think about your coordinates on a vertical line. Pretend your line was right here. Maybe this point is 4, 2, and this point is 4, -3. Well, the x values are the same. If you subtract two values that are the same, what do you get? 0. So when the x values are the same, you're dividing by 0. You can't do that. So they say it's undefined, the slope. What else? So, we found an equation in y equals mx plus b. Let's try this one. So what I'm trying to find now is the equation of the line that goes through the point 2, 3. And I'm trying to find two lines that go through it. The one that's perfectly horizontal. So I'm looking for this one. And then I'm also looking for the line that's perfectly vertical. And those two lines don't have an equation in y equals mx plus b. It's a little different. Horizontal lines are just y equals and then a number, like we did on the projectile motion. We graphed y equals 50. We had a horizontal line, kind of like this, perfectly straight at 50. And then x equals a number, which you can't do on the calculator. That's vertical. So, anyone think they know the equation of the horizontal line that would go through the point 2, 3? Yeah.
Y equals 3.
Yeah, it's just y equals 3. That's the equation of this line right here. It's a horizontal line at 3. And how about the equation of the vertical line that goes through the same point? Yeah.
X equals 2.
X equals 2. So those are just kind of special cases. Make sure you don't mix up x and y. Y is horizontal, x equals is vertical. It's very easy to mix it up because you think of the axes, but that's just how it works. Point slope. No, not point slope yet. So you could have an equation like that. 2x plus 3y equals 6. Now, what I could do is I could get y by itself. It's not by itself. All right, so if I subtracted 2x from each side, I could get 3y equals, and I could do it this way, negative 2x plus 6. And then I could divide everything by 3. But the point is, why am I doing this? Why would I want it to say y equals negative 2/3 x plus 2? Why is what I circled better than what I started with? It's the same thing. I just move stuff around. Yeah.
It's nicer to look at it. Or
Okay, why is it nicer to look at? Yeah.
You could use on the graph.
Why can I use this on a graph easier than the other one?
Y-intercept and slope.
Yeah, I've got my slope and I've got my intercept, so I could easily plot my intercept and then just go down 2, right 3, and put a few more points. I can't really tell that from the original. So you guys should be comfortable with taking something that doesn't have y by itself and rearranging it so it does. Okay. Point slope form is another equation. I don't use it as much as y equals mx plus b. But it's y minus y1 equals m times x minus x1. The advantage of point slope is what letter isn't there that we had in the other equation of a line? Yeah,
B.
you don't have b. You don't need it. All you need is exactly what the name of the formula says. You need a point which goes in here and here, and you need a slope which goes in right there. Be careful if x1 or y1 is a negative, because if you minus a negative, it would become a positive. But here is a perfect problem where you could use that formula. Find the equation of a line that has a slope of a half, that's your m, and it has to go through the point -2, comma 3. -2, comma 3. So you never fill in for the x and the y. Only fill in for the y1, the m, and the x1. And if you didn't want to use this formula, you could get around it with using y equals mx plus b. It'd be a little more work, but you could. So in my example, it's going to end up being y minus what?
1 minus 3.
Yep. Equals. And what's going to come after the equal sign?
0.5.
Yep, 0.5 or 1/2. And then x,
-2 or 2.
y 2.
Because there's a negative for x1, so
Yeah.
because negative plus negative equals positive.
So when you subtract a negative there, it's going to come out positive. And that's it. That's the equation of a line in slope intercept form. Now, is y by itself there? Could you get it by itself if you wanted?
Yeah.
Yeah, this one actually wouldn't be too bad. You could start by doing something like that. Now it's in neither form. It's kind of in between slope-intercept and point slope. You distribute the 1/2, and then you could just add 3. Now the directions did not say to do that. I'm just showing you another example of how you can get y by itself. And now you get your y-intercept. That's why you might want to do it. All right, so last 2 things. Parallel, perpendicular. If 2 lines are parallel, what do you know about them? Like, how would you tell that they're parallel, like, numerically? Yeah.
Their slopes are the same.
Slopes are the same, and
They never intersect.
yeah, they never intersect, but something has to be different. The y-intercept. 2 lines are parallel if they have the same slope and different intercepts. If they have the same slope and same intercept, then they're not parallel to the same line, right on top of each other. So that's parallel. Does anyone remember perpendicular? It's actually 2 words. Doesn't matter about their y-intercepts, but it's something about their slopes. Parallel is same, but perpendicular is blank, blank. Part of it is flipped, that's half of it. Yeah.
The opposite, inverse.
Opposite, what do you call it when you flip it?
Inverse or
Yep.
Reciprocal.
Yep. Opposite reciprocal. So if you had a line that had a slope of 2/3, the opposite reciprocal is negative 3/2. All right, so this is where you would see a question on the test having to do with parallel or perpendicular. I'll probably pick one, not both. But this says, write an equation of a line that's parallel to this one. And the line that you give me the equation for has to go through the point 1, -2. So I know this is stuff from like geometry and algebra 1, but sometimes people just don't remember parallel, perpendicular stuff. So what's the first thing you would have to know about this equation if you're going to find a line parallel to it? Yeah,
The slope.
you got to get the slope. So the first thing you want to do is what we've done a couple times. Get y by itself. 2 steps. What would be my first step to get y by itself? Yeah.
Subtract 3x to 5.
So subtract 3x from both sides. And your last step. Yeah. Divide by what? Yep, divide by -2. Everywhere. That's gone, that's gone. Now my negatives here cancel. So what's my slope?
3, 2.
Yeah, 3/2. Yep, just 3/2, no x. Okay, 3/2. So my slope is 3/2. What's x1? 1. And what's y1? -2. Now, what you're doing right there is exactly what we just did right here. You've got a slope, you've got an x1, you've got a y1. Just fill them in and see what you get. So it's exactly the same thing. Only difference, you had to figure out the slope first. Other than that, it's the same. All right, and I think that's it. Last thing. So the last thing is linear inequality. So this big idea is like when you have a line, sometimes it's solid, sometimes it's dotted, sometimes you shade above, shade below. That's what I'm talking about right here. So 2 things you have to know about the line when you draw it. It can either be solid or it can be dotted. How do you know? You look at your problem. If it has the less than or equal to, greater than or equal to, you draw a solid line. If not, you draw dotted. And that's actually it. That's all the steps. Then, once you draw your line, you either shade below or shade above. Okay? Shade below for these 2. Less than or equal to. I think less than, I think under. Greater than or equal to, shade above. So if you wanted to graph this one, would it end up being solid or dotted?
Dotted.
Yep, it would be dotted. And what might you want to do first?
Figure out where the shade. Or put it into the slope.
Yeah, I would say if I was going to graph that, I would probably put it in Slope-Intercept first. Get y by itself. Draw my line. And then I would end up shading under. But that's how you would do that one. We can look at one of those tomorrow if we want. Okay, so I know that second section, that had a lot of stuff in it, but I hope like slope, rise over run, like most of that's from Algebra 1. Okay, so homework, page 31, that's the first part we did. So 32 to 36. 45, 52, that's a 52, and 55 to 57. And then page 42, the problems just kind of jump around. so we'll take a look at that tomorrow, and then we'll look at last two sections, Tuesday and Wednesday, to finish up chapter 1.